I left you with the thought at the end of yesterday afternoon's lecture that the refractive index could be negative. And I also reminded you that the refractive index could be associated with this mysterious quantity, Einstein's metric, which measured how much space was squashed or stretched. And I invited you to reflect on what would happen if you stretched space so much that the metric became negative. So I'm going to air some of those issues today, and let's see how far we get with your challenge of seeing how much we all understand this. I'm sure I don't understand it all, and that's the intriguing thing about physics, that physics progresses by continually plunging yourself into areas which you do not understand, going beyond your comfort zone. And if you don't understand everything, as has been said, that's good, because that's your training to be a physicist. You have to be comfortable with the uncomfortable, because that's the way we make progress. It's resolving those issues that is what research is all about. So we saw this guy yesterday, and this is his day, because I'm going to talk about focusing light. And a guy who had something to say about focusing light was Fermat. Fermat was a genius who delved into many areas of science, and many of his contributions were inspired in the sense that they were basically guesses. There's the Fermat's lemma, which he postulated about prime numbers, and which has only been proved in the last 10 years. But here's another contribution he made. So you can think of a lens as refracting light here, here, and here, and say, well, it does what it does because of Snell's law. But Fermat had a more general principle of how light gets from A to B. He said that light takes the shortest optical path between 2 points. Now, clearly, if you're talking about a lens which focuses light from the object, from the image, this trajectory here is not the shortest geometrical path, but it is the shortest optical path if the optical path is defined as the geometrical path times the refractive index. And if you make that definition, then you'll find that all these trajectories which the light actually takes through the lens satisfies this minimum requirement. Now, the basis for that is the wave theory of light, and it didn't exist at that time. So Fermat made an extremely inspired guess, and we're going to talk about, so far we've been talking about the propagation of light in terms of geometry. Electromagnetism is almost pure geometry. It couldn't exist without a geometrical basis. And so this picture which Fermat gives us is going to underpin much of what I shall say today. So what's the problem? Well, Galileo labored hard to make lenses as perfectly as he could, but people gradually realized that however much polishing and scraping you do, there's ultimately a limit to how good a lens of this form can be made. And the reason is that this is some technical argument here, but I'll give you a more straightforward argument. The reason is that not that light doesn't have structure in it on a very small scale. If you shine light on this surface and you go in there with some instrument that can measure the electric fields around the atoms, you will find a detailed structure in those electric fields, even down to the atomic scale. So the structure is there in the light at the surface. But only part of that structure can escape. There's a limited amount of information that can escape from a surface. And that information is contained in what we call the far field, because it's the light which is reflected from the surface. But very, very close into the surface, there's another sort of light called the near field, and that remains glued to the surface. It decays away from the surface very, very strongly. And it's in that near field that all the little wriggles of where the atoms are and so on and so forth, all that information is locked away in the surface. And even the finest lens cannot get at it. And it turns out that the limit to the resolution is the order of the wavelength of light. Maybe a half, maybe a quarter, or something like that. But that's the order of things. And this is a huge limitation in conventional optics. For years, the optical microscope was a tool of choice for looking at the very small. Hooke built, the Royal Society built the best microscopes of the age, and he looked at extremely small biological specimens. His drawing of fleas and so on and so forth are quite remarkable. But when you want to go smaller than that and look inside the cell, or even look at the DNA molecule, the optical microscope fails you because all the details in which you're interested are below its resolution capabilities. And then there's the electronics industry. You can't possibly look at the details on a computer chip with an optical microscope. You have to use some other form of imaging, such as an electron microscope, because the details written are simply smaller than you can see with light. So it's a great challenge to improve the resolution of light. But in this respect, this phenomenon of negative refraction to which I alluded can help. So what is negative refraction? This is Snell's law, and it's defined in terms of the ratio of the sines of these two angles here. And conventionally, light comes in on one side of the normal and exits on the other. So this will be a positive angle measured round here. But if the angle goes on the other side of the normal, that's classified as negative. So when this one's positive and that one's negative, making this chevron shape here, that's the signature of negative refraction. Of course, then the sine of a negative angle is a negative number, and the refractive index from this formula is negative. Now, why am I making a big deal of this? You have all done algebra at school, and the whole point of algebra is that if x equals whatever, you can put it in the formula and it works and everything comes out just fine. But this isn't mathematics, this is physics. And it sometimes matters when you change the sign of a number, you may get completely different physics. And what I want to show you is that altering the sign of the refractive index and making the light go this way rather than that way sure changes the physics. And to show why, I want to refer to this diagram here. Now, I explained yesterday that there are two velocities to light. I think it came up in the questions. I need some chalk, actually. At the end, right. At the end, rummage, rummage. Little box.
Down the side.
Down the side. Great. Yes, thank you. Okay, so the first velocity we'll talk about is the wave velocity. So light consists of waves. You package it in little pulses, but inside the pulse, it's chopped up into waves. So I'm going to have some waves incident on the surface. Here are the wave fronts. Here's the surface. And they're headed this way. And when I have waves in the other medium, then I have to match the wave fronts across the surfaces. So the crests of the waves have to come at the same point. So these lines start here. And the normal to the waves must point in a negative direction. However, these waves are moving, so they have a velocity towards the surface, and parallel to the surface, they're actually moving in that direction. And so if you are going to keep that matching condition in time, these waves must also have a component which is heading in the same direction at the same speed. And so if we match the wave velocity, or the phase velocity, or whatever you like to call it, then they must point like that. This elementary matching condition of the wavefront requires that when we match the waves, the wave velocities both point towards the surface so that their parallel components are equal in the same direction. Now, the other velocity is the velocity with which energy flows. So if we imagine that these waves are put into a little packet, and that packet is flowing towards the surface, so nothing strange in the vacuum here, the waves and the packet just move with the same velocity, then the energy flows towards the surface. Now, we have to be extremely careful here, because when that packet gets into the negatively refracting medium, if the packet flows in the same direction as the waves do, then you're into a nonsense, because the energy source is in here, pumping energy towards the surface, and then something mysterious here is also pumping energy towards the surface. That's not a causal situation. So what we have to have is that although the energy flow is definitely this way in the vacuum, because we understand the vacuum very well, the energy flow here has to be in the opposite direction, because the energy flow must always be away from the source. You can't, it's a nonsense to say that energy flows into the source. That isn't a source, right? So this is a very, very weird material, and I can show you that on the next slide. So that's just the thing writ small again. Here's the pulse, and the energy flow and the wave flow are in opposite directions. So the pulse heads this way, and the waves head this way. It's as if they're wriggling, trying to get out of the back of the pulse. Okay? And as I suggested yesterday, if you want to see something like that happening, throw a stone in a pond, and the ripples will travel at a different velocity from the envelope of the ripples. You can see that effect. So that's the first weird thing, that these negative refracting materials, without really doing any math, you can immediately see that something strange and not quite the physics we know in the lab is happening. In fact, nature has no examples of a material which shows negative refraction. And when it was first suggested in the 1960s by Victor Veselago, it caused a lot of excitement, and a lot of people said it couldn't exist because they didn't agree with all this analysis here. And it was debated hotly at that time, but the debate died out simply because you couldn't find any naturally occurring materials with a negative index of refraction. And that's really a lesson to all theorists like myself, that you can have as fancy a theory as you like, but if at the end of the day you can't do an experiment on it, it's going to be in a book on a shelf gathering dust, and people will forget it eventually. So experimentation and ultimate translation into making something is the very essence of physics, at least so I believe. Now, another thing you can do with negative refraction was also realized by Victor Veselago years and years ago. He realized that if you have this chevron type of negative refraction, then the rays are naturally turned back to the axis, and so naturally come to a focus inside that material. In fact, they come to a focus twice, because they go negative refraction at this second surface here, so you actually get an object and two images, if the sample is thick enough, of course. Now again, just drawing ray diagrams isn't so impressive, but now imagine that you're in the Hotel swimming pool, okay? Or maybe you don't have any children, but if you do, one day you may take them to a swimming pool. You may be worried about their safety. Now, here's a tip. What you need to do is to pour some fluid into the water that turns its refractive index negative. And then what happens is that instead of seeing your kids in the water, because of Veselago's lens, your kids are suddenly swimming in the air above the water, and you can see everything that they're doing. So, just like that. Yes?
You actually don't see anything in the pool of water. It just looks like water. And the things that are actually in the pool, you can't see them because they look like they're above the pool.
Okay. That diagram there is a fake, okay? Because in order to see something in the water, you've got to be looking at the water itself. But it's as if the water had projected an image above the water. You don't actually see anything in the water. You can't because of all these rules and things. It's not such a weird thing, actually. If you look at a curved mirror, then that curved mirror will focus things in thin air above its own surface. So there are instances when you do get things floating in air which occur naturally with mirrors. But I like this one. What? No. Well, it doesn't look as though it's in the water. You see what's in the water, but not as if it's in the water. Oh, sorry. Yes,
Just a little bit on the detail. Shouldn't it be inverse this way as well?
Yeah, it looks this way, so it does invert, yes.
As in, shouldn't it be the opposite way as well? Not really flipped over.
I think it's
horizontally as well.
Yeah.
I think it's turned. What?
Shouldn't it be flipped horizontally as well?
No. I think that's right. What I did in Photoshop, right, was to mirror this fish in this surface. Did I do that right? Did Photoshop do it right?
No, as in, I mean, like, in the hypothetical situation that this is possible,
Yeah.
it should be flipped the other way as well, right? Not only mirror.
The head and the tail should be flipped on.
The tail should be on the left. And the
No, it should be like this. Yeah. You see why in a minute. Okay. Anything else? Yes.
So finally we see that the parallel component reverses direction in negative refraction.
Sorry?
Parallel component reverses direction. I mean, you have the slide.
Yes.
This formed in the parallel component.
Yes.
This one reverses direction. Will you use a metamaterial?
I don't quite understand.
This is a normal material. You have a ray of light.
Okay, this is a bit technical. I think you best write it down, and I'll deal with that at the end. May we do that?
While I have a short break, I might even just do
Okay.
It's flop. Hold on one second.
You want me to put the timer?
Yes. We're formal. I'll try.
Okay. I'm always frightened of deafening people when I'm shouting. I hope I'm not doing that. Right. So I intended that to be a 5-second distraction, okay? You never know what will catch people's eye. So let's get a bit technical. How do you make something with a negative refractive index? Well, Veselago told us how to do that as well. He went right back to Maxwell's equations. And actually, Maxwell's equations don't work in terms of the refractive index. They split light into its electrical and magnetic components. So what they care about is the electric and magnetic response. And they are determined by the electrical permittivity and the magnetic permeability, which just tells how much the material responds to electricity or magnetism. And it turns out that the refractive index is the geometric mean of the product of these two quantities here. And normally, these quantities are positive, so when you take the square root, you have a positive number here for the refractive index. That's conventional stuff. But what Veselago showed is making arguments of causality and so on, like I've invoked here. He argued that if both of these quantities were negative, taking the square root is like taking the square of minus squared, which is minus, okay? So he said if both of these are negative, although you've got something positive inside here, you must put a negative number out there. There's two choices, plus or minus. You must take the minus charge when both epsilon and mu are negative. So that was his recipe, but the problem was, as I've indicated, that this requirement is not satisfied in any natural material. And so it happens that if we look at all the possibilities of material response to light, then you can divide it into 4 quadrants according to whether epsilon is positive or negative, or mu is positive or negative. Now let's think about let's set mu equals to 1, no magnetic response, and think about epsilon. If epsilon is positive, that's an ordinary dielectric like glass or water. If epsilon is negative, that's like a metal. It happens when the electrons are free to rattle about inside the metal. And what are metals? We all learn that metals are sonorous and lustrous. They shine. And they shine because they reflect light. So light can't get very far into a metal. And that's because epsilon is negative. Now it turns out that if we set epsilon equal to 1 and let mu vary, then when mu is positive, it's just normal business. We're up here. But when mu goes negative, you also get an opaque region for similar reasons to the material being reflecting when epsilon is negative. So you have these quadrants here which are reflecting. They have their own interests, but they're well understood. But then there's this 4th quadrant, to which we have no experimental access, or did not until recently, where epsilon and mu are both negative, and the refractive index is negative. And I've already given you some hints as to this region being very mysterious. So people are itching to get their fingers on it. And I say it's like the secret garden. Perhaps you know the story of the secret garden. It's about a little girl who goes to a dark moor in Yorkshire. They don't get darker than moors in Yorkshire. And she's an orphan, and she's sent to live with her uncle, who's a manic depressive, and she wanders around this place a bit, and she encounters a wall, and the wall has a door in it. And eventually, she finds the key that opens the door, and inside is a wonderful garden full of roses and so on and so forth. Lovely story for kids, and this is our secret garden. And recently, we found the key of how to get in, and the key is the concept of metamaterials, which I've introduced to you already. And metamaterials, I remind you, work not just with atoms, but they make sort of artificial atoms by structuring the inside of the material on a very fine length scale, which sits between the wavelength of light and the atomic region. So these structures must be smaller than the wavelength, because what you want to do is the wavelength to take an average over them. But of course you can't have them smaller than atoms, because otherwise it wouldn't be a structure. So these are meta-atoms, if you like, and because we can now choose their structure be anything we like, the possibilities for engineering them are much, much greater than they are if you're just limited by the periodic table. So it turns out that we can engineer structures like this, which was built to some of the designs we made in Marconi, but we didn't build it. It's David Smith who did it at UCSD. And what we have here are little rings with a magnetic response and wires with an electrical response. And it turns out that they have a negative response to both electric and magnetic fields. So epsilon and mu are both negative. How can that be? How can you push something this way and it goes that way? It's nonsense. Well, it's not nonsense if you think it in this context. These structures are designed with what we call resonators. So when you excite this with an RF field, this is designed to work with radar waves. Oh, sorry, I should tell you the dimensions. The dimensions are about 5 millimeters here, and this structure is responding to radar waves with a wavelength of about 30 centimeters, something like that. No, 3 centimeters, shorter than that. So well sub-wavelength. So, but why should these structures give a negative electrical response? They're little resonators, and a characteristic of a resonator is that it swings the energy from one form to another. In this case, these resonators are at one instance sending current around a current loop, and that makes the magnetic field. But at the same time, they're charging a capacitor, so the energy is tossed about between the capacitance and the inductance. And when you tune the frequency of the radiation through a resonator, the sign of its response flips. Now, I can give you, I should have brought a swing along actually, but in the days when your mother took you to the park to play on the swings, perhaps you remember that the swing is a sort of resonator. So you can sit on it, give it a push, and it will swing to and fro. And the resonance there is the exchange of energy between the kinetic energy of the swinging motion and the gravitational energy when the swing comes to its highest point. And you swing backwards and forward. Just leave the spring like that, swing like that, and it's a natural resonator with the frequency of its natural swing, like a pendulum. Now, if your mother's a cautious person, she might push the swing gently this way and gently that way, and as she pushes, the swing goes as she pushes it. But if your mother is in a bad mood and has had too much coffee that morning, she might shake the swing like this, and then what you will do is that. Try it with a pendulum. You'll find that if you shake it faster than its natural frequency, it will in fact go in the opposite direction to that which you push it. And that's exactly what these little resonators do. If we tune to a frequency slightly higher than their resonant frequency, the magnetic field is actually opposite to the direction in which you're pushing. Really weird. And the same with electrical resonator. And it's this trick that we deployed to get negative magnetism and negative electrical response. And this was the first structure made with a negative refractive index, albeit responding to radar waves at a few gigahertz of frequency. Now, a computer simulation of what that structure does shows that here's some wave packets coming on the surface, and they refract at the surface, and you can see that the beam here is very clearly headed off into a negative direction. Now, the San Diego group measured their data, and it was, the first negatively refracting structure, so it didn't look quite as clean as this. To my mind, it definitely showed negative refraction, but there were the doubting Thomases. And there was one paper written in Physical Review Letters which said, refraction, always positive and never negative. And there was a long screen saying why David Smith and I were a couple of idiots for believing Professor Lager in the first place. And since DARPA, the Defense Advanced Research Projects Agency, were funding all this work, they got extremely nervous at all this criticism. So they commissioned the people at the Phantom Labs in Boeing to construct a huge apparatus to measure this with some precision. So here's the Boeing thing. I mean, it takes cranes to, here's a crane that lifts all this stuff. These are two microwave horns. This is an ordinary optical table. And in here the Boeing team are going to lower a prism, or just like Newton's prism, you know, where they did the colors experiment, a prism which has a negative refractive index. And then they're going to look at what angle the light is refracted here. So here are their samples. This is the metamaterial with a negative refractive index. And just to show that they're not cheating, they had a positively refracting sample made of Teflon, actually, of exactly the same shape. And then they measured the deflection of light in that apparatus with those two samples. So here's the Teflon, and here are the data as a function of angle. There's 0 degrees, and the Teflon clearly moves the radiation through a positive angle. But you swap that for the metamaterial, and you can see that the peak in deflection comes at a truly negative angle. And that experiment was regarded as definitive, and all shouting died away. And even if the people who criticized didn't agree with that, they fell silent, everyone. That was the radar waves. Again, it's much more difficult to make these metamaterials at high frequencies, but I'll just show you a couple of examples of what people are doing at higher frequencies. This is designed to work at optical frequencies, and now you see this ring-type structure. Actually, this is referred to as a fishnet structure. It's a bit like a fishing net. And this gets its negative refraction from currents flowing around these loops here. This is how it looks like when you make it out of layers of silver, magnesium fluoride, and this has been shown to have a negative refractive index in the visible region. The only problem is that because of imperfections in manufacture and the fact that these materials aren't perfect conductors and perfect insulators, you have loss, and that's always a hassle in these structures which are resonant. So the very latest work in metamaterials and negative refraction is to introduce some gain media. So you can put some organic dye here, you pump it like mad with a pump laser, and that hopefully will provide enough amplification of the light to compensate for any losses in the silver and other materials here. So that's the direction things are going experimentally. But now I want to return to my theme of a perfect lens and how negative refraction can help us. As I explained, an ordinary lens is restricted by the wavelength because it only captures part of the information coming from an object, from a surface. It captures only the far field, and that has information only enough to give you this limited resolution. And what we have to do if we want to make the resolution better is to look at this near field. So I explained that there is lots of intricate detail in the electric field of the light, but it's locked to the surface. It decays exponentially away from the surface, and a few microns away, it's almost undetectable. It certainly doesn't take part in anything an ordinary lens can do. So what you need is an amplifier. You've got to grab this weak signal, boost it up so that it comes to the same level as it was in the object by the time it reaches the image. And that's a tall order. So you're asking from a passive material, which is a lens with no batteries in it or anything, you want it to be an amplifier. And that's a pretty difficult thing to achieve. Nevertheless, it turns out it can be done. So it turns out that if you make a Veselago lens and you arrange that the refractive index is -1, exactly -1, it only works if it's exactly -1, then the resolution of this lens is unlimited. And the reason is that it can grab this near field, it can do that amplification process, and dump that information into the image plane to give you the perfect resolution. Now, I had that idea in the year 2000. Victor Veselago knew that his negative refractive material could make a lens. What he didn't realize was that it could be perfect. And I was head of a department at that time, and I didn't have much time for research, but one wet Sunday afternoon in March, I think, I sat down on Sunday afternoon and did the calculation of what the lens would do if you asked it to focus this near field. And the answer I got was that it would focus the near field, and I was astonished. What I expected to come to was the conclusion that the lens didn't do that, but it will be an interesting reason why it should not do so. But the answer contradicts, so that really scared me, because I knew that the entire optics community would rise up as one and say, nonsense, and that's certainly what some of them did. And if they were right, then instead of being famous, I would be infamous, and I wouldn't be here talking to you today. I'd be on the retirement bench in a park somewhere. Fortunately, it turned out in the long run that people agreed with this, but there was a huge furore and a fight. And I learned something quite a lot about science politics at that time. And one of the things that I learned was that whatever happens, however rude people are to you, you keep your cool, and you're always polite to them, because at the end of the day, if you are right and you've kept your cool and the other guys have made a great fuss, they've actually done you a favor, because it gets into all the press, and what the press really like is, well, they like writing about science, but what they really like is writing about people fighting. Okay. But pick your fights carefully. Pick them so that you can win. This one we won, I'm pleased to say. And let me explain why it should be. There are several ways I can tell you about this, but I'm going to use Fermat to explain these things. So Fermat said that the light takes the shortest optical path between two points. And he said the optical path was a geometrical path multiplied by the refractive index. And all these paths are the shortest paths. So let's say thank you, Professor Fermat. What happens in the Veselago lens? So I'm going to, the refractive index is -1, so these angles are equal and opposite. And if you do your similar triangles, these triangles are similar, and therefore these lengths are equal. So as I go from the object to the first instance, I have plus d1 and another d1 here, but minus d1, because this is a negative refractive index. So the distance from here to here is 0. It's not even a minimum. It's 0. And no other lens can do that. And so, in the language of Fermat, the object is the image. It looks as though, to the light, you've compensated for all this stuff in between, and as far as the light concerns, it's back to where it started. Now, Fermat's result was a guess, so it may have been approximate at the level of the ray theory, blah, blah, blah. But what turns out is that if you take Maxwell's equations, you calculate something called the transfer matrix. And all the transfer matrix does is it takes, if you know the electric and magnetic fields in this plane here, Maxwell's equations are a set of differential equations which can be integrated, and you integrate them and transfer those fields from the object plane to the image plane, that's a transfer matrix, then the transfer matrix you can show is unity, because the integration through here is cancelled out by compensating integration through this bit here. And so at the level of Maxwell's equations, the object is the image. And that's why the lens is perfect, because Maxwell says it should be. And in fact, there's a general rule which says that if you have a medium, and epsilon mu can be anything you like in here, and you have a second medium next to it, construct it so that for every point here, there's a mirror image point where you invert epsilon and mu. So if you have plus epsilon and mu here, then at the mirror image point you have minus epsilon and mu. Then these two halves will compensate for one another. Now, you may say, well, big deal. I've seen Wrigley light before. It goes wiggle, 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 and you unwiggle it on the way out here. Yes, I understand what you're saying. Good, good. But like many things to do with negative refraction, there are paradoxes. And here is another paradox. So my great friend David Smith, who's been my partner in crime these last 10 years, said, well, if your theorem's such a big deal, what does it make of this? And he constructed this system, and it looks very like the Vestlager lens, except he's taken a chunk out of it, he's taken a cylinder out of the lens, and he's plonked that cylinder at the mirror image point here. But he hasn't destroyed the conditions for the theorem, he's mainly changed them. So we have plus epsilon plus mu here, minus epsilon minus mu, and here we have minus epsilon minus mu and plus epsilon plus mu. So it's still sort of negative mirror images, one of the other. And so the theorem says that if I shine light on this, it should go straight through. No problem here. If let's do it in the ray approximation, and this shows you the limitations of the ray theory of light. So the ray theory predicts that it goes straight through there. Good, good, good. That's what it should do. So what are this? So this ray comes in, we apply Snell's law, and it's reflected. No deal. But Maxwell says it should go through. How the hell does it go through? Well, let's go a little further. Let's just supposing it did get through. So on its way, it might get to here. Now, what would it do if it was here? It would kind of get trapped here. That's what we call the resonance. Okay, the light's going round in circles, just as it does in those resonant cavities in CERN that you heard about on Monday, I think. Yes. So the light's in a resonant cavity here. It's going round in a circle. And that's where we want it to be. So what happens? Well, when you switch on, the first thing that happens is this. And you say, oh, damn, the theorem's not working. Well, yeah, wait, because the ray theory is an approximation. You can never make an infinitely thin ray. It's always got a little bit of a tail on it. The narrowest you can do is a Gaussian beam, which is about as thick as a wavelength. A wavelength, again, dictates how thin a ray can be. So these rays have little tails on them. And resonances are awfully good at picking up little tails. I don't have a champagne glass here, but fortunately for you, I'll be even more incoherent. But if my voice were an octave higher and I had a champagne glass, and I had a very powerful voice, I might be able to sing at the champagne glass and smash it. And that happens because if it were a champagne glass, I'm stretching your imaginations here, and I flicked it, it would have a resonance. And if you send sound at an acoustic resonance of the same frequency, then the resonance will just say thanks and pick up that energy and pick it up, and eventually the energy in the resonance will grow and grow and grow until it's limited either with one thing, either you smash the glass, or if the glass isn't very good quality, you'll get enough loss in the glass that it compensates the energy you're feeding it. And the same thing happens here, that the little tails on these rays couple to this resonance here, and that grows stronger and stronger and stronger. So your friend who's watching and laughing at the failure of your theorem will gradually see this reflected. So this resonance, of course, will feed out into here eventually, and this beam will become stronger, but it will also send a negative amplitude here, which will cancel this guy here, and the beam will go straight through. But you have to wait. So it's like the Cheshire Cat. You know, your friend was laughing at himself. Eventually, you win your bet after time when this thing goes through. Now, David, although he was teasing me, had already done the simulation to show that the theorem is right. So here is, what is it? It's a cylinder with some negative refractive index in air, probably, or something. And it's scattering like mad, so there's waves all over the place. And then he puts this compensating layer here, and the waves should go straight through without lots of reflection. And you can see there's quite a bit of disturbance here where we're excited in resonance. You see the odd splotch of red here, which is a sign of very high intensity resonances. And when all this mucking around is done, the waves come in and they go through smoothly. So the theorem does work, and it's just the paradox that the ray approximation is just that. It's a very dramatic illustration that approximations don't always work, and sometimes they give you nonsense. Well, I did stress the importance of experiments. Have people done experiments on this? Well, it turns out that although you can't get exactly the conditions at optical frequencies of negative refraction, surprisingly enough, for many purposes, a perfect slab of silver metal will do the job. And Jiang Zhang of University of California, Berkeley, he was at that time actually in Los Angeles, but he's now moved to Berkeley. He did this experiment, which was to test whether a lens could focus less than the wavelength. So the first thing he did was to make an object, and the object was a 50 nanometer thick chromium film. And on that film, he'd made a grating with a spacing of 60 nanometers, and that's 6 times smaller than the wavelength of illumination, okay? He also put the word nano here. And then there's a spacer layer, and then there's an almost equal thickness of silver, which is acting as a lens, and then of course, you can't see the image because it's too small to see with your eye or with a microscope even. So the image was written in photoresist, and when the experiment was done, all this stuff was stripped away, and the photoresist developed, and then the image was viewed, not with a microscope, with what's called an atomic force microscope, which is a little needle that just scans over the surface and sees if there are any bumps there. And this is what they saw. So here's the scale, 500 nanometers. You expose the system, and you can resolve the grating. Perhaps better to the eye is this experiment here. So there's the original chromium grating, and here's what you see if it's all spacer layer, if there's no silver in the system. So you see this is quite blurred, and if you scan over this image, you see that the resolution is just the same as the wavelength. The wavelength is about 360 nanometers, so it's blurred. Next, they do the experiment with the silver in it. It's like putting your glasses on. The whole thing goes ping, and you sharpen up, and now you have a resolution which is a sixth of the wavelength. So that was the first optical experiment. There have been experiments in the microwaves verifying the perfect lens. Another one was you might ask, why isn't it perfect? Why is it just sub-wavelength? It's already a big deal to be sub-wavelength. And the reason is that the way this, I explained the function of a perfect lens to you in terms of Fermat's principle and Maxwell's equations and so on. But what's actually happening in the lens is the following. That what you have to do is to take this near field, which is decaying very strongly, is very weak, and you've got to amplify it. And it turns out that the surface of silver is full of little resonators. They're called surface plasmons. And the tail of these very weak signals couples to these surface plasmons, and the energy builds up to just the right level to make, it's wonderful how the mechanism all sort of fits together if you get the parameters right, but it does. But that's assuming that the silver has no loss in it, because loss destroys the resonance. If you've got lots of energy rattling around in a metal, if that metal has some resistance, then the resonance won't do its job. And so what limits the resolution of this so-called perfect lens is not the aperture, which would be with a microscope lens. It is, in fact, the presence of resistive losses in the metal. So to get around that, people have gone to materials which have less loss, and one material is silicon carbide. It works at a much lower frequency in the infrared rather than the visible. And so these guys published a paper in Science in 2006, and here is the negatively refracting stuff, silicon carbide, and actually the spacer layer has been split into two, the two layers of silicon of equal thickness, and what they're looking at is a structured layer of gold below. And the idea is that if this is really a lens, this whole system should look as though the gold is here on this top surface. So all this should vanish, and the gold should appear on the top surface. So if you scan over it with a tip, and you bounce some light off that tip, then the tip should actually see these things on this surface here and image them. Here is the image of the holes in the gold, successively smaller, and you can see these easily. These you can see, these you can't really see those. The wavelength here is much longer than before. It's 10 microns, but you can actually, these objects are a 20th the size of the wavelength. So that lens has less loss in it, you get better resolution. Okay, so that's a perfect lens, and the challenges awaiting people for the perfect lens are to tackle the perfection with which you make the lens. So before, no point in trying, the wavelength was a limit, polish your lens as much as you want, you won't do better than that, forget it. But now, the gates are open. If you can make a better lens, it will perform better, and there is theoretically no reason why you shouldn't keep on trying and get the resolution better. So people are looking for more perfect materials, they're trying to make the surface flatter. It's a difficult problem, but people are making progress with it. And when they're done, they'll be able to image whole areas of materials at a resolution much higher than we can now. In the final minutes of my talk, I want to go back to this transformation optics theme with which I opened in my first lecture. So, okay, it's a big deal that you can get a lens that has a perfect image, but at the end of the day, it's really rather a boring image, because usually you want a lens to do something like make something bigger, or to write a very fine structure on a surface and make it smaller. But this lens, because it's perfect, has the image exactly the same size as the object. But remember transformation optics. And what transformation optics says is that if you have a situation in which you have some electric fields, rays of light, magnetic fields, and you want the geometry to be different, put it on this Einsteinian rubber sheet and pull it around a bit, stretch space a bit, and you can make it any shape you want, and then you go back to Einstein's equations for epsilon and mu, and he will tell you what values in epsilon and mu you can use to make that situation. So without talking in riddles, we can take the original perfect lens with a flat lens, an object, and an image, and I can bend the flat lens round into a cylinder or an annulus of a sphere, you choose. And then what I get is I've stretched all this space on this outside of the curvature, and inside the curvature I've squashed the space, so I've actually made a magnifying glass. And I'll show you that in a moment. But there's something even more intriguing. One can have a view of the perfect lens itself in terms of this metric of space. So I'll show you that, and then I'll get onto the magnifying glass. So let me give you the transformation optics view of the perfect lens. So I'm going to do some origami now. Our Japanese friends won't be too impressed with my origami. It's not very complicated. But they would be impressed if I could do it for real. So I'm going to take some ordinary flat space like this, and I'm going to make it out of rubber. I'm going to squash it. So as I squash it, this internal region here that I'm squishing up gets a higher and higher refractive index. So the light comes through exactly as it was before, because I'm not squashing this region, but it does a little fancy jiggle here because the refractive index is no longer unity. As I squash more and more, the refractive index higher and higher. And then eventually, I squash it to 0. And the refractive index is infinity. And mathematicians know what happens when you go through plus infinity. You go to minus infinity, okay? And then you come down the slope, and now you've got a piece of negative space. And remember, Einstein told us that the metric of space is the refractive index. So if you've made some negative space, you've made some negative refractive index. So that bit in between has a negative refractive index. But look, it's really weird space. You've tucked space in on itself. You have made triple-valued space. So as let me have a picture of that. As the light goes through the lens, you think it's doing that. But what the light thinks it's doing is going forwards. It's going into this nip and tuck bit of space here and coming out again. And that's why it sees the image once here, twice when it returns, and a third time as it emerges from the other side. And that's the geometric interpretation of what the perfect lens is doing. Okay, so that's what I promised you to talk about yesterday, of negative space. Anyway, let's have some more fun with transformation optics. So here's what you can do. Here's the transformation, if you like transformations, that takes you from a flat plane maps you into a spherical annulus of negative refractive material. Inside, you've squashed all this stuff into a highly refracting region here. And the function of the lens, this time, is to take all the contents of this inner sphere here, outlined in green, and viewed from outside, it's a bit like the swimming pool, you know, with a fish above it. All the contents of this inner bit here appear outside to be in this outer ring here. So you've made something which is really quite small appear much bigger than either the lens or the object itself. So they're a very peculiar sort of magnification. What's more, you do this perfectly. Every detail is reproduced. Now that creates another paradox for us. And I can explain it this way. So here comes the light. It goes through the negative refracting stuff and it comes out the other side. Okay. And the idea is that this lens is going to capture all the light that hits this big red sphere, and it's going to capture it and put it inside here. So that's great. It captures that ray. Negative refraction, captures that guy, lets it go again. Captures this guy, lets it go again. What about this one? It's supposed to catch it, but it doesn't hit the lens. How can it capture it? I'll go back to that slide I show you of David's paradox and ask what would happen if the light got in here. And that's the secret. So the light comes along here, negative refraction, negative refraction, negative refraction. There are lots of resonances here, which are sitting on those states to which we want these rays to have access. So we want to put these rays in here. And the way they get there is by remembering that they're not infinitely thin. They have little tails on them. The little tails couple to these resonances, and eventually, with time, if you wait, the resonance will build at an amplitude, and you will see these guys in here. And the proof of that is that if you solve Maxwell's equations, you send in some wave field from the left, that wave field is compressed here. Now, I have a video of that, but if anybody has a tendency to epilepsy, please close their eyes, because this is really weird. No, seriously, if you do, please close your eyes. Is that okay? Oh. I'm sorry, this has come out too big.
There we go.
Okay. So this is an animation, and what you have is the wave field coming here, and you have this sort of optical turbine thing, which is capturing the waves and stuffing them into this smaller volume here. And you know that you can see this continuity of the wave fronts here as you compress things. Notice something else, that although the energy is consistently flowing from left to right, what I'm plotting here are the wave fronts, and they flow inside the negative material from right to left. So they're going in the opposite direction from the energy. And the energy in this region here is going in the opposite direction to the waves, and you can see it just circulating around that inner region there. So that's the optical turbine, and I'm nearly done. So you can open your eyes now. So what can we use that for? And I'm almost on my last slide. So there are many devices in optics which only work in the ray approximation. So they've got to be really big relative to the wavelength. And one of them is the shadow. So if I have a point source of light, and it's working, and I have an object in the way, a sharp shadow will be formed if the object is much bigger than the wavelength of light. If it's not, the wave nature of light will curl round a small object, just the way water curls around a stick in the stream, and it will rapidly fill in the shadow on the far side of the object. Small objects cannot create shadows. However, we have a lens that can make small objects seem as though they're large. It can make them seem as though they're larger than the lens or the object itself. And so my student Wei Sheng Wei has, so what we have here is the, what he's got in here is a very, very small black object. And it's small compared with the wavelength. The wavelength you can tell by the spacing between these wave fronts here. Here's a wave coming in from the left, and around it he's wrapped a perfect spherical, actually it's a cylindrical lens, it doesn't matter, perfect cylindrical lens, whose magnification will make this black object appear as big as this. Now remember, this region here is just empty space, but you can see when we solve Maxwell's equations that if you throw waves at it, instead of creating a tiny shadow, it creates a really big shadow like that. So, in conclusion, I hope I've told you about some new tricks in a very, very ancient subject, standing on the shoulders of giants, indeed, but there's still plenty of interest and fascination in this ancient and wonderful subject of optics. Thank you very much.